Welcome to my talk about hole profiles. I am Anna Palisson. I am a consultant engineer and I offer consultancy services to develop steel cold form sections and structures as well as composite slabs in accordance with the Eurocodes. I'm presenting here the design by calculation as developed within the GRISP project for profiles with a circular or a square hole. After a brief introduction to the topic, I am going to present the state of the art before the GRISP project in order to help you understand why the present methodology was developed. I am also going to describe the extensive test program which was performed in order to provide the required data as well as provide the results of the testing analysis. Then, I am going to explain the methodology to calculate the effective section of a flange with a hole and the moment resistance of a profile with a hole in the flange under compression. This methodology is proposed as an amendment on Eurocode 313. Lastly, I am going to introduce the Excel file which was implemented to calculate span moment resistance for a profile with a circular or a square hole in the flange. Let me introduce the topic of the present talk. On these two pictures, you can see a steel profile which is commonly used in structural roof decking. The picture on the left shows a profile with a circular hole, and the picture on the right shows a profile with a square hole. Such holes are required in the upper flange for the passage of services. The holes may be circular or square, as you can see on the pictures. They may be of different sizes. Generally, there is only one hole in the profile. The design rules for profiled sheeting without a hole are provided by the current version of the Eurocode 313. The standard stipulates that the effects of local and distortional buckling should be taken into account in determining the resistance of cold form members and sheeting. Local buckling effects should be accounted for by using effective cross-sectional properties calculated on the basis of the effective width according to Eurocode 315. In determining resistance to local buckling, the yield strength Fy should normally be taken as Fyb when calculating effective widths of compressed elements according to Eurocode 315. As we noticed on the previous slide, the design rules are only given for profiles without a hole. In addition, as far as the studies found in literature are concerned, they show that holes decrease the strength of a profile locally and globally. But they do not provide any information on calculation of the moment resistance. Thus, at the beginning of the GRISP project, we could observe that despite the frequent presence of a hole in the upper flange, no information was given by the Eurocode or by the literature on how to take a hole into account when designing a steel profile. Actually, the only way to design such products is to carry out tests according to Eurocode 313, but such tests are expensive and time-consuming. So, we could confirm that there was a real lack of data and relevant knowledge on how to determine the resistance of a profile with a hole, and that an innovative methodology was necessary. This state-of-the-art has allowed us to define the GRISP project objectives and the methodology to be applied to achieve them. The main goals were to provide the missing technical data and, of course, a calculation method for profiles with a hole. The methodology consisted in determining the missing data through a huge testing program and in developing and validating a calculation method with the test results analysis. This method was proposed as an amendment on Eurocode 313. Now let's discover the extensive testing program performed within the GRISP project. The first aim was to determine the resistance values of different types of profiles, which we can see on the pictures. The tests were performed on profiles without a hole, with a square hole, and with a circular hole. The second aim was to compare the values obtained for profiles without a hole with values for those with a square hole and for those with a circular hole. The third aim was to assess the impact of a hole on the moment resistance of the profile. The final aim was to define a calculation method for profiles with a hole. The tests performed within the GRISP project were single-span tests as defined in Annex A of the Eurocode 313. We can see the configuration on the picture. Here we can see the pictures taken during the testing. On the left we have a profile without a hole, in the middle a profile with a circular hole, and on the right a profile with a square hole. The observed failure mode for all the profiles was a local buckling of the upper flange near the midspan. The moment resistance was determined. The results obtained for profiles without a hole, with a circular hole and with a square hole have allowed us to make comparisons and to assess the impact of a circular hole and a square hole on the moment resistance. The major results found out was that the same size circular and square holes induced the same decrease of the moment resistance. You can see on this table the decrease of the moment resistance according to the size of the hole. The next step in our scientific process was to come up with a calculation method for moment resistance. For the profiles without a hole, the moment resistance was calculated according to the Eurocode 313, and the effective width of the flange area was calculated according to the Eurocode 315. This standard stipulates that the gross cross-sectional area, AC, is defined as follows. ACF is equal to ρ multiplied by AC, where ρ is the reduction factor for plate buckling, and in this case, ρ is the reduction factor for flanges regarded as internal compression elements. Therefore, in this case, the effective width B was determined according to Table 4.1 of Eurocode 315, given for internal compression elements. As far as profiles with a hole are concerned, as said previously, no design rule exists. The testing results showed that when the diameter of the circular hole D is equal to the width of the square hole W, as on this picture, the influence of the hole on resistance moment is the same. Therefore, the same model of calculation was proposed for a square and a circular hole, depending on the width of the hole in the flange section. We have proposed to calculate the moment resistance of the profile as the sum of the moment resistance of ribs without a hole and of the moment resistance of the rib with a hole. To calculate the moment resistance of a rib without a hole, the effective width of the flange area was calculated according to Eurocode 315 by multiplying the gross cross-sectional area LC by ρ, where ρ is the reduction factor for flanges regarded as internal compression elements. Therefore, in that case, the effective width B was determined according to Table 4.1 of Eurocode 315, given for internal compression elements. To calculate the moment resistance of a rib with a hole, the effective width of the flanges area was calculated according to Eurocode 315 by multiplying the gross cross-sectional area RC by ρ, where ρ is the reduction factor for flanges, which are not anymore regarded as internal compression elements, but as outstand compression elements. Therefore, in that latter case, the effective width B was determined according to Table 4.2 of Eurocode 315, given for outstand compression elements. Eventually, the moment resistance of hold profiles, determined by calculation as defined previously, was compared to the moment resistance defined by testing. This comparison confirmed that the definition of the moment resistance as the sum of the moment resistance of ribs without hole plus the moment resistance of the rib with a hole gives safe and current results with the testing results. These results allowed us to submit an amendment proposal on Eurocode 313 consisting in the addition of a new section entitled Sheeting with a Hole in the Flange. This amendment stipulates that, in case of a circular or a square hole in the compressed upper flange, the effective width of the flange parts adjacent to the webs may be determined as outstand elements of width BP. For the final part of this presentation, I would like to introduce the Excel file which was implemented within the GRISP project to calculate the span moment resistance of a profile with a circular or a square hole. This file was developed to provide a design procedure in order to encourage and facilitate the use of hold profiles. This file was validated by comparing its results with the testing results. Moreover, this calculation method has been made available to a number of industry users to check their relevance with the purpose. Yes. Thanks to this tool, you will be able to calculate the span moment resistance for a profile with one hold rib in the upper flange. To conclude, it is important to underline the following points. Firstly, this design by calculation method was supported, checked and validated by a huge testing program performed within the GRISP project. Secondly, an Excel file was implemented including this method in order to calculate the span moment resistance for a hold profile. Lastly, this method was proposed as an amendment on Eurocode 313. I hope I have contributed to making you more familiar with this methodology. I invite you to follow my 3 other talks related to perforated profiles, steel decks with embossments, and steel decks with outward stiffeners. I thank you for your attention.